All right, so in this work example, we're looking at work, energy, and power, and it starts off with a definition, define power. You can define power as the rate at which work is done, or the rate at which energy is converted, the rate at which energy is transferred. Okay, those are all good ways to define power. Great, now that's going to be in YouTube. That little noise there. And, oh, just got me now. Start over. No. We'll edit it out later. Although I forget. Now this whole explanation will be in there. Sorry, YouTube. Define power, the rate at which work is done, the rate at which energy is converted. It's always good, like I said, in a problem study to remind yourself whether these quantities are vector or scalar, because you'll have questions on the midterm or on the final exam that will say, like, underline all the vector quantities, circle all the scalar quantities. So to know which quantities are vector and scalar is also useful. So does anybody remember for power? Did anybody put that down in their definition? Power is a scalar quantity. Very good. Defined as the rate at which work is done, or the rate that energy is transferred or converted from one form to another, and it's measured in watt is the unit of power. No question. All right, so a scalar quantity defined as the rate at which work is done, measured in watts. Right, so put all that down. That's a good mark right there. But just saying the rate at which work is done is enough to earn the mark. State what is meant by gravitational potential energy. We'll just ignore that one. The equation that we use in this level of physics for gravitational potential energy is mgh, but that shouldn't stand as your answer. Okay, that's how we calculate it. But what does this really mean? It means a mass in a gravity field has energy due to its height, its position. So we want to kind of state it that way. The energy an object possesses due to its position in a gravity field. Contrast that to the elastic potential energy conclusion that you've been working on this week with your lab work. That's energy an object possesses due to its shape. Like we change the shape of an object, like a spring, we can press it or stretch it out, it gains energy. Equal to what? The work done. The work that we do lifting an object is still force times displacement. So the force is the weight mg, the displacement is vertical, so height. That's, about the 7th time we've emphasized that idea, right? Like this comes from the more general definition of work, but it's just a unique displacement, right? So only the force exerted in the direction of displacement contributes to work. That's an important idea that we'll sort of need again here. So energy an object possesses due to its position, right? Its height, h, in a gravity field with strength g. Massive objects have energy. So you can use the equation to help guide your thinking, but don't just put mgh as your answer, just because that's what I wrote down. Try to sort of put that in your own words. A note to your future self, if you had this same question on the midterm, you'd be able to go, oh yeah, I wrote that down already. I already have good answers for that. So energy an object possesses due to its position. Objects have potential energy either due to their shape or their position. Gravitational potential energy is energy due to an object's position. This is an approximation. It's what the more general equation for potential energy becomes when we're close to the surface of the object creating a gravity field G. This is the actual equation for potential energy in physics. There's a negative sign in front because we define maximum potential energy. If we could take this mass and separate it from this mass by infinity, which isn't really possible, right? But theoretically, we can hold that idea up in our mind. Two masses separated by infinity, they're the furthest away they're ever going to be, right? If they could somehow be an infinite distance away from each other. We define that potential energy as 0. So these objects have 0 potential energy. As they get closer, they lose potential energy, right? Like the potential energy decreases. Like you drop an object in a gravity field, its potential energy goes down, right? It's converting it into kinetic energy. And so all potential energies are negative. Now, when we do our calculations here in like Physics 101, okay, AS level physics, this is an A level physics idea. So not even in ACE physics, AS level physics do we need to deal with this. This is an A level physics. Do we start to deal with that? In astronomy, we kind of need this. Imagine a height so far above Earth's surface that it no longer falls down to Earth and develops kinetic energy, but rather floats off into space and falls towards the sun or the moon or something like that, right? Depending on which way we go, we could lift an object up so high in Earth's gravity field that it basically is no longer part of Earth's system anymore. It's closer to the moon, it's going to fall towards that. So we need a better way to deal with potential energy for, you know, things that are just beyond the surface of Earth. This is good here close to the surface of the Earth. Like this becomes that, okay, when we're close to the surface of the Earth. It behaves the same way. So this is a nice approximation we use in this level of physics. And either one is fine to recognize that every two objects in the universe, all two objects in the universe have some amount of potential energy between them. And it's equal to this, right? So if you know how massive the things are and you know how far away they are, you can calculate how much potential energy there is between you and anything else. Another galaxy, Earth, sun, whatever. All right, the question goes on to tell us an aircraft of mass 1,200 kilograms climbs upwards with constant velocity, 45 meters per second, as shown in figure 3.1. The aircraft's engine produces a thrust force of 2,000 newtons, 2.0 by 10 to the 3 newtons, 2,000 newtons, to move the aircraft through the air. The rate of increase in height of the aircraft is 3.3 meters per second. Calculate the power produced by the thrust force. It's really easy to sort of go down a path that's not productive, but it's helpful to sort of do that, to sort of try a calculation out and sort of, is this going to get me here? Or do I know enough to sort of solve it this way? But as we're going through it, we want to have some general problem solving strategies at our disposal here. So I would always tell students to write an equation down that has the thing you're solving for in it, because then it can kind of roadmap the solution. Power is the rate that work is done. That's where we defined power, you know, originally. So it's work over time. You may recall that work is force times displacement. And we've seen in the past that an alternative equation for power is to substitute in what S over T is equal to. Displacement over time is the same thing as velocity. So force times velocity is a valid equation for power. We're given a velocity and we're given a force. So if you knew to multiply those two numbers to get this answer, well done. That's all you had to do there. Sometimes students just guess, like, here's a number, like whatever, multiply some things, divide some things, you like get lucky and like, I multiplied these two just by a lucky guess. That would have got you there. So it's 2,000 newtons times 45 meters per second. A Newton meter per second, well, a Newton meter is a joule, and a joule per second is a watt, right? So watts of power. And so if you multiply 45 times 2,000, you get 90,000, right? 9 by 10 to the 4. Pretty straightforward if you have the ideas in mind, right? But it's almost impossible, or it is impossible, if you don't know how to define power, right? So we've talked about it in the past where, you know, you get some marks for defining it, but you need to be able to apply that definition to calculate something, to do something sort of worthwhile with it. So 90,000 watts of power produced by the thrust force, because all of that force is in the direction of displacement, right? So remember, like, work is force times displacement times the cosine of the angle between them. We were just mentioning that with the potential energy, like the work that we do is only against gravity in the vertical direction. So we apply a force vertically when we lift, you know, an object's weight, mg. So these vectors are in the same direction, so we don't need to worry about it. Like, that's the direction of the thrust force and the velocity, so it's their product. Moving right along. All right. The advice I want to give to students in class and students maybe watching this on YouTube preparing for their ACE exams is on ACE paper 2, where there's introductory prepositional phrase here, determine, comma, for a time interval of 3 minutes, comma. So they're introducing these next 3 calculations with that. So keep that in mind. Like, for these next 3 calculations, we're going to determine for a time interval of 3 minutes. So that's relevant, right? They're telling us that for a reason. In fact, a lot of the language in this is very important. It seems like, well, that's very specific. Okay, it's an aircraft moving through air. Like, that's actually important, right? The fact that it's crashing through air. This is key language right here, constant velocity. Like if the bell didn't go off in your head when you read that, it should. Okay, you should say, oh, that means something. Constant velocity means something here. That's important language too. So let's go ahead and calculate the work done by the thrust force. The advice I just gave a moment ago was if you're solving for, work, write down an equation that includes it. So work equals force times displacement. That's a good equation for work. We also said that like work is the change in kinetic energy. So maybe you have that sort of equation down, the work kinetic energy theorem. So well, maybe we can use this to solve it, but it's actually this one, right? Because it's a by the thrust force. So that's given. So that's kind of nice. They tell us this, 2000 newtons. And we have to know the displacement. If they don't give us the displacement like they give us the force, it's not that friendly of a question, right? Like, what is the work done if the force is this and the displacement is this? They must have given us a way to calculate it, though. It's just one of those two-step problems. So it's like, oh, we got to use this equation to solve for the displacement, then plug it in here and solve for that. Who knows an equation for displacement? If you start going into your big four equations of motion, and you start going, well, V equals U plus AT, but that's actually the one without displacement in it. But I know that V squared equals U squared plus 2AS. Maybe I can use that to solve for it, or S equals 1/2 U plus VT, or S equals UT plus 1/2 AT squared. That's kind of overkill. That's good review because it's like, oh yeah, the big four equations of motion, they have displacement in it. But is there any acceleration going on here? Constant velocity, right? So we really just kind of want this equation, but make the acceleration 0 and go, oh yeah, distance equals rate times time. Velocity is just displacement divided by time. We're just using the velocity equation. We know how fast it's going, 45 meters per second. We know how many seconds it's going, kind of. I mean, we know it's 3 minutes, and hopefully you know there's 60 seconds per minute. So the displacement here is just the VT. It's just the velocity, 45 meters per second, times the time, 180 seconds. Right, 3 minutes. So this gets back to the idea of base units, right? Having just units that agree. If I need to know Newton meters, which are joules of energy, then I can multiply a velocity in meters per second by seconds to cancel that out and get meters. So this thing has undergone how many meters of displacement? It's very clear from the figure, the path of the aircraft. Like it's actually being displaced along that line there, labeled path of aircraft, right? Like, okay, that's the displacement vector. It's going that way, right? And if it's going for 180 seconds, 45 meters every second, it's helpful to talk through it like that, to really remind yourself like, oh yeah, that's what distance is. It's I'm going a speed for a certain amount of time. That's how I move places. Like you've done it this morning, right? You made it here to class. People watching on YouTube are like, I didn't go. Well, go somewhere, get outside. Hopefully the sun is still shining. You're not living in some doomsday future. But YouTube is still going, so okay, at least that. All right, so this is 8,100 meters. I think that's what that works out to be. Times 2,000 newtons. 2,000 newtons times 8,100 meters. What's that? I'll use my on-screen calculator. All right, so we got 2,000 times 8,100, and then 1.62 by 10 to the 7, or you could think about significant digits, 1.6 by 10 to the 7 joules. So this is 3.0 minutes, right? They sort of set the significant digits right here. So you could probably record 1.62 or just 1.6. The increase in gravitational potential energy, we can use the sort of approximation, MGH. That's the only equation you need for gravitational potential energy at the AS level physics or in pre-ACE. So the mass they gave, 1,200 kilograms. The acceleration due to gravity, 9.81 newtons per kilogram for the gravity field strength, how much newtons of force per unit mass. And then the height, we have to calculate similarly to how we did this. So this was the actual velocity along the displacement it was traveling, but they told us some bonus information. They tell us that it was climbing at a rate of, so in the y direction, it had a rate of 3.3 meters per second. And so that information was given in the question. So the height is the vertical displacement, right? So the velocity in the y direction, they tell us was 3.3 meters per second. And again, all of these calculations, 1, 2, and 3, start with the precursor determined for a time interval of 3 minutes. So we've got still 180 seconds of climbing 3.3 meters every second for 180 seconds. It means we've traveled how far vertically? What's our increase? 3.3 times 180. So we get our height, 594 meters. We're that much higher up in Earth's gravity field. We have that much more potential energy. Just based on the position of that aircraft, it's got, it's increased its potential energy by that amount. So that's 9.81 per kilogram. And this is still 1200. You multiply all those out and the units kilograms cancel, you get Newton meters, which are joules. So always sort of check to make sure the units work. 594 times 9.81 times 1,200 is that number. But please don't write that down on your answer line. So you could say, okay, I calculate this to be 6,992,568 joules, but that's pretty much just 7 million. All right, 6.99 million, 7 million. So again, this is dealing with significance. Okay. Avoid the temptation to, like, I want the answer as precisely as my calculator has it. That's too precise. Okay. You don't want to over-report the precision of your answer. All right. Now the next calculation is, what is the work done against air resistance? So it's for the same 3 minutes. Okay. There's work done against air. And here's where we can refer to the essential question on the chalkboard. Why is it important to understand the law of conservation of mass energy? Like, matter is neither created nor destroyed, energy is neither created nor destroyed, and matter and energy are really the same thing, E equals mc squared. So that quantity, mass hyphen energy, is conserved. If we look at the calculations we just did, and let's clean it up a bit, 1.6 by 10 to the 7 and 7 by 10 to the 6. Okay, something should bother us about these values. Let's see. We said the work done was 1.6 by 10 to the 7 joules, but the increase in gravitational potential energy was only, what was it? 7 by 10 to the 6. This number is less than this number, okay? And so we had up here a minute ago, work is the change in kinetic energy. So like, where did that energy go? Energy is neither created nor destroyed. If that engine is doing work, it should show up as kinetic energy somewhere. All right. Don't look at this and go, oh, wow, we just destroyed energy. Yeah, there's some energy here, joules of energy, and look, not so many anymore. Nice, we've just destroyed energy. You know that energy can't be created or destroyed, so we got to keep track of it. Like, where did it go? Well, work is energy. There's work done against air. Okay. And so it's a 1-mark question. It should be a very straightforward calculation. It shouldn't be anything we got to, sort of wrestle with for too long. We go, oh, okay, look, one calculation leads to the next. If this is the work done by the engine, some of it went into increasing the potential energy of the aircraft, that much of it. But did the rest of the energy like speed up the aircraft? Did it accelerate? I mean, that's one thing that we could say, well, maybe it accelerated it. It changed the kinetic energy of the aircraft itself, right? Like the aircraft went from 45 to 46 to 47, but it didn't. How do we know? Because again, it tells us constant velocity. So this thing is not picking up any speed. Rather, it has a force going this way. There must be a force going that way that balances it. And that force we know that opposes motion traveling through air is the drag force. So like there's a drag force, the air is doing work on the aircraft, or the aircraft is doing work on the air particles. The change in kinetic energy is the kinetic energy of the air itself. right? Like we're heating up the air. As this aircraft barrels through air, this like 8,100 meters worth of air, those air particles are getting hotter, right? That energy is still in the universe. Just because it doesn't show up in our aircraft as either potential or kinetic energy doesn't mean it's lost to the universe, right? So that's why it's important to understand this law of conservation of mass energy. You know, that question is, I forgot to put it up there first period. I'm like, oh yeah, we needed a question because I had to erase the board and it was all, you know, kind of a drop. You guys are lucky, you get both the essential question and the problem study. You're on YouTube and you're like, well, I want to see the chalkboard. Just follow me on Instagram. Okay. I haven't updated it yet, but like I said, it's a couple more. I'll get it there by the end of the day. Dr. Schleich, all spelled out. So we got an energy budget. We got to account for the missing energy. All the rest of the energy, because it isn't kinetic energy of the aircraft, it's energy in the air particles. So it's work done against air. So we have 1.6 by 10 to the 7 minus 7 by 10 to the 6. We're just subtracting those because all the rest of the energy must be there. Okay. I mean, it could have been sound energy or something like that, but that still is in the air, right? So it's work done against air resistance. All right, what does that work out to be? Anybody do that one yet? Nine by 10 to the 6. Anybody else calculating that? That seems right. 16 minus 7. 9. There's a 16 by 10 to the 6. 16 by 10 to the 6 minus 7 by 10 to the 6. 9 by 10 to the 6. That makes sense. 9 million. All right. Calculation goes on to say use your answer in part 3. So that's the 9 million to calculate the force due to air resistance acting on the aircraft. All right, so we want to know the force, right? The force due to air resistance, and we know the work, right? We calculated the work as 9 million joules, so 9 megajoules. So work is force times displacement. We want to know the force, we know the work. Knowing the equations, more than half the battle in physics, but knowing how to correctly substitute in the values that are important, that's the rest of the battle. Remember when we did projectile motion and we had to solve for sort of like when the projectile got to here, we knew something about its motion at that point. So we say, okay, well, that's the point where it's both at maximum height and where its y component goes to 0. It's like when we plug in 0 into the equation, v equals u plus at, 0 equals the initial velocity minus 9.8 t. So we end up solving it for the initial velocity and it ends up just being like, oh, add this term to both sides. U is 9.8 t. When we did physics field day, I said, here's the easy way to just computationally calculate your y component of velocity. Multiply your t by 9.8, where t was the time to max height. Well, why do we have to use that time? Because that's where that y component goes to 0. Like this is the actual equation we're using. We can just sort of simplify and say, well, as an algorithm, it's this 9.8 t. If you don't care where it comes from, just multiply your time to max height by 9.8. The reason why that works is because of this more general equation of motion and the substitutions we're making. So we have to correctly, now that's just a lengthy, sort of review example for why it's important to know sort of what displacement do I substitute into this to solve it. It's very clear what work, because it says use your answer in part 3. So, okay, that's the work, 9 by 10 to the 6. It's clear I'm solving for force. What displacement? Does anybody know? If so, leave it down in the comments below. Or if you're in class, you can raise your hand or call it out. Yeah. Yeah, but we calculated a displacement for parts 1 and 2. So yeah, you're right, but which one? Should we use the vertical displacement or the actual displacement? Yeah, because if you think about it, like it's barreling through air along what vector? Let's go back to our figure here. Again, it's very clear. They label it path of aircraft. Where is it crashing into air? Where is it doing work on air? Along this path, right? The 8,100 meters of displacement. So again, you just kind of think, well, I'm doing work against all the air I'm crashing into, not just a component of the air, which is like a theoretical thing we can hold up in our mind. So yeah, we're going to divide each side of this equation by the displacement 8,100 meters. And we'll see what that gives us. So we got our 9 million. 500. A joule per meter is a Newton, because a joule is a Newton meter. I get it. Ones repeating. And so the two significant digits, I could report it like that. You like all those ones, I can't resist, 1111. It's, I don't know if you can see it. Well, I guess now I'm not sharing enough of my screen for you guys to see that this is November 4th. If I remember to upload this today, then you can see, oh, we uploaded on November 4th. So 11/11, that's coming up here. That's Veterans Day. It's my son's birthday. Happy birthday, Isaac. Last one, with reference to the motion of the aircraft, state and explain whether the aircraft is in equilibrium. I think everybody in class that has good notes on the conditions for equilibrium and read the question carefully should be able to answer this. Okay, let's get these 2 marks, even if some of the other calculations weren't that forthcoming. Hopefully the definitions were there, like, yep, define power, got it. State what is meant by gravitational potential energy was a bit tougher because we couldn't just use the equation. We kind of needed to say, oh, it's the energy of an object due to its position in the gravity field. Can anybody, with reference to the motion of the aircraft, state and explain for both marks? So you got to make a statement. It's either in equilibrium or it's not. But then you got to explain it for the second mark. Anybody know? Is anybody very confident? They're sure, I've got it. I don't want to call on you. I want to call on somebody who's like not too sure about it. Like, I think it might be this. Let's try to like clarify your thinking. What are we thinking, class? There's some adequate wait time for those watching on YouTube in the distant future so that they can leave a comment down below. Don't forget to hit that like button. Get on the Dr. Schleich notification squad. All your ACE physics needs met right here on this channel. In order for an object to be in equilibrium, it has to meet 2 criterion. And in your notes, you know what it says right there. Oh, conditions for equilibrium, no net force, no net torque. There can be no net moment. Now, this question is not about moment of force at all. So we can say, okay, there is no net moment, check. Is there a net force? Is there a resultant force? Let's use that word. A sum of forces would be a resultant force, a non-zero resultant force. If there is a net force, then an object will accelerate. That's always true. That's the law of motion. Net forces lead to acceleration. Is this object accelerating? How can we determine whether it's accelerating? We can't just say, well, it must be. Have to use the clues in the question, which indeed. Now, why is this? I guess my computer froze here. Oh, there we go. So yeah, if you read the question carefully, with a constant velocity, as soon as you read constant velocity, immediately you as a student of physics should say acceleration is 0, there's no net forces. It's always going to be true. Okay, if it's constant velocity, then it's not accelerating. Constant velocity means no acceleration. What is acceleration? The rate of change of velocity. Just because it's moving doesn't mean it's not in equilibrium. Things that are in motion is just as natural as rest, okay? An object in motion will remain in motion. Objects moving, they maintain their current state of motion. So they'll just move with constant velocity. They won't accelerate. A net force is required. So because we sort of use the right side of this, because we know there's no acceleration, we can deduce that the net force is 0 or the forces are balanced. The thrust equals the drag, the lift equals the weight. All the forces acting on that aircraft are balanced. There are forces acting on it. It's moving, but it's moving at constant velocity. And so we'd say, yes, the aircraft is in equilibrium because there is no net force. Now, the resultant force is 0. Or you could say, yes, the object is, or the object is in equilibrium because it's moving at constant velocity. There is no acceleration and therefore no net force. You're trying to get to the criterion that says, I have to show that there's no net force here. The way to prove that is to just restate, like they told you, there's constant velocity, no acceleration. You kind of want to get that in your own words. 12 total marks on this one. This has been another worked example with Dr. Schleich. We'll see you next time.